Hi, I'm Fiona.
And I'm Temi.
Today we'll be talking about You Are Who You Know, Inferring User Profiles in Online Social Networks. Most of us have Facebook profiles. Even if we don't have all of our information on our profiles, can our friendships actually reveal the information we intended to keep private? We'll begin by talking about one study, You Are Who You Know from 2010. This study examines how we can predict attributes of a user from their social network presence. More specifically, we can predict unspecified information about a user just by looking at their Facebook friends' available information. This has widespread implications about user privacy or lack thereof. For example, I have a Facebook profile. Given the Facebook network I belong to, including people I am and am not friends with, what information, like college that I attend, year I graduate, etc., can you find out about me based on my friends' public information? The study uses two data sets obtained primarily from Facebook. They collected information such as friends lists, college majors, and year of graduation.
Before we talk about predicting user information, we will explore the motivating observations that researchers made about the data. First, users are significantly more likely to be friends with other users who share their attributes, which is the idea of homophily. This study showed this using a measure called affinity, which is the ratio of the fraction of links between attribute-sharing users relative to what would be expected if the attributes were assigned randomly. The second observation is that dense communities center around these shared attributes. Researchers used a metric called modularity, which measures the strength of division of a network of communities or modules. Modularity is then a measure of the fraction of intra-community edges minus the expected value of the same quantity in a network with the same community divisions but with edges placed without regard to communities.
Using affinity and modularity as described in the last slide leads us to the final piece of this puzzle, rating the strength of a single community. Measuring the strength of a community, given that we know that communities form around attributes, will allow us to predict the likelihood of the members sharing that attribute.
We want to show that if we have a dense community and we have some users' attributes, we can infer the unknown attributes for other users. In order to do this, we need to first find a metric to help us build out a community from a set of known community members. One standard metric for rating the quality of a single community is metric conductance. We define graph G with vertices V and edges E. A is a subset of the vertices that form a community due to a known attribute. B is the subset of vertices not in A. EAB is the number of edges between A and B. EAA is the number of edges within A. The conductance of A is EAB over EAA, and this measures the strength of a single community. In this case, a small value means a strong community because this means lots of links within the community, with few links spanning different communities. However, this method is biased towards larger communities with more edges, and therefore not comparable across graphs of different sizes and densities.
So, the solution is to normalize conductance. First, we define a new value k that is a modification of conductance. K is the ratio of edges within A over the sum of total edges for A. Then, to obtain normalized conductance, we subtract k by the expected value of k for a random graph divided into specified communities A and B. Randomizing means that we keep the same community division and degree distribution, but all links are placed randomly. This normalized conductance ranges between -1 and 1, with strongly positive values indicating significant community structure and negative values indicating less community structure than a random graph. The algorithm for community detection takes in a subset of users S in a community and the social network graph G. We greedily add nodes by maximizing normalized conductance at every iteration. First, divide the graph into two components, A with known members of the community and B everyone else. Then, select the user from community B that results in the highest increase in normalized conductance C for A, and add this user to A. This stops when no remaining user would produce an increase in the normalized conductance C for A. Return community A as the result. The performance of this algorithm, along with other most popular algorithms, is dependent on real-life communities actually forming around this common attribute. In cases where strong communities do not form, such as around undergraduate majors, these algorithms perform poorly. This approach outperforms other algorithms by using normalized conductance instead of modularity, allowing for the detection of both small and large-scale communities. We can compare algorithm performance using the metrics precision and recall. Precision is the amount of nodes correctly identified as community members out of all the nodes the algorithm identified. Recall is the amount of nodes that the algorithm correctly identified out of all nodes in the community. This algorithm is able to detect undergraduate years of graduation with high recall and precision. And the other common algorithms have high recall but low precision because they essentially return the entire network. The most significant finding from this research is that given as few as 20% of users with known attributes, the remaining users' attributes can be inferred with over 80% accuracy.
Going back to the example that we started with, let's assume that Fiona belongs to a small Facebook network with 20 users. We don't know any personal information about Fiona. We also know all the friendships that exist in the network. Let's say that there is a sub-community of exactly 10 users who go to Emory. We know that Temi and Daryl go to Emory because they have it public in their Facebook bio, and we want to know the remaining 8 users that also go to Emory. Using the greedy search algorithm, we begin with the Emory network of Temi and Daryl. Then, for each remaining user not already in the Emory community, we calculate the normalized conductance if we were to add the user to the community. We add in the user that results in the largest normalized conductance value for the Emory community. We then repeat this process of greedily adding users to the network. We terminate the algorithm when normalized conductance does not increase for any additional user. At the end of the algorithm, we will have determined all of the 10 users who go to Emory, only using the network friendships.
The 2019 paper, Deep Adder, Inferring Demographic Attributes via Social Network Embedding, shows that past community detection models fail to take into account the correlations that exist between demographic attributes, which leads to a lower precision performance overall. Instead of focusing on community relationships, this paper focuses on relationships between attributes. They've demonstrated their methods significantly outperform other methods for both single attribute inference and multi-attribute inference on a large-scale social network.
The study You Are Who You Know found that we can utilize relationships in an online social network to infer unknown information about a user, given that we know 20% of users who belong to a community centered around a common attribute. This has important implications. First, we can enhance user experience on social networks by filling in missing attributes and improving suggested friends and targeted ads. Second, your private information is not truly private. Data controls fail to protect a user from personal content being leaked by friends. This idea is explored further in the article Unfriendly, which examines the dangerous implications of conflicting privacy settings. This also means that if a hacker obtains Facebook information about your connections, they will be able to infer more about you than what is on your profile.
Thank you for watching. Are there any questions?